131 PMP emitter allows us to now see what happens to the LED as I move the adjustable resistor away from me with the PMP transistor attached. And the LED is now connected to the emitter portion of the NPN transistor. The lamp would be less bright than project 130, than the previous project. Should not be as bright as in project 130, but as bright in 129. 132 is NPN collector motor. We have the motor with the fan on top, and I will set the adjustable resistor in the middle and turn on the switch. Now the motor will not spin on most settings, but when the RV switch is closest to the R1 resistor, the motor will spin. It's possible that it may not if your batteries are low. In that case, you should replace your batteries. The fan is connected to the collector part of the NPN transistor. 133 is NPN emitter motor. I'm going to move the adjustable resistor away from me, and the fan is now attached to the emitter on the NPN transistor. Now the fan eventually spins, but I will tell you that it will not spin as fast as in the previous project, just like the lamp would have been dimmer when it is attached to the emitter rather than the collector of the NPN transistor. Project 134 is buzzing in the dark. Be aware this might be a little loud, but I'm going to insert this battery and you will hear a very high-pitched sound from the whistle chip and speaker. Now when I cover the photoresistor with my hand, the circuit now makes a buzzing noise rather than a high-pitched one. When I remove my hand and light reaches the photoresistor again, the frequency of the sound will increase. When I cover the photoresistor, resistance increases and less current can flow through the circuit. 136 is high frequency touch buzzer. I replaced the speaker with the red LED, although in reality I would use the 6-volt lamp, but I'm going to put my finger between these two connecting points, and the buzzer will make a quieter and more pleasant buzzing noise as the red LED lights. And it may flicker very fast too. Project 137 is high frequency water buzzer. I connected 2 jumper wires to these connecting points, and I'm going to put the ends of both of them in this bottle of water. Now in reality I would use a cup of water, but because this bottle of water is right with me, that's what I'm going to do. Now the buzzer makes a very high-pitched sound as the red LED comes on. And water conducts electricity, water itself conducts electricity much better than my finger. Just try not to let the ends of the jumper wires touch each other, or that will ruin the fun of this circuit. 138, Mosquito, requires you to reinsert the photoresistor, and now the circuit should sound like a mosquito, the buzzing sound. Does it sound like one to you? To me it does. Project 139 is high sensitivity voice doorbell. You will see that we have the microphone included, and I'm going to put in this battery and music will play. I'm going to wait for the music to stop playing. In the meantime, I'm going to place the circuit over here. And now I'm going to try to make some loud noise and watch what will happen. I'm going to zoom in. the music plays again. The microphone is responding to the sound, and it is very sensitive in this circuit, so even if you're a few feet away, you may still be able to get the music to play. I was just slapping my leg with my palm. Let it play one more time. And there you have it. 140 is louder doorbell. I replaced the LED, which would normally be the lamp, with the antenna coil. And now, when the circuit plays, the music will be louder. .141 is very loud doorbell. I replaced the antenna coil with the speaker, and now when I trigger the music, it is much louder than in the previous project. .142 is doorbell with button. I'm going to insert this battery and the music will play. I'm going to wait for it to finish playing. And now I have to push the press switch to get the music to start again. Just quickly press and release it, and there you have it. It's just like a regular doorbell at your house, although in reality you probably have to hold the button down to keep it sounding. If you let go of the button, the sound will stop. Here you just push it once and the music will play all the way on its own. For project 143, darkness announcer, you would replace the press switch with the photoresistor. And now, after the music plays once, you're supposed to cover the photoresistor and the music should play. But it doesn't when I cover it. I don't know why, but supposedly it would play once to announce that it has gotten dark. Now, if the speaker is too loud, you can replace it with the antenna coil. 144 is musical motion detector. I replaced the photoresistor with the motor, and after letting the music play once, I'm going to turn the motor in either direction, and the music plays. I'm going to try it counterclockwise since I spun the motor clockwise. And yet, once again, it will play again. Project 145 is radio music alarm. For this project, you're going to need an AM radio, and any plain AM radio will work. Then you'll need to tune the radio to a station that is not broadcasting, where there's mostly static. And then with this circuit, you're going to turn on the slide switch. And can you hear music playing? No, it's not coming from the circuit, it's coming from the speakers on the radio. You can do it again. Then you can tune your circuit for best reception. Once again, the music you're hearing is from the radio, not the circuit itself. And I know it's pretty loud and you can still hear a lot of static, and I don't know why the sound was distorted the second time. What you can do next is connect the jumper between these 2 points, and then you could use a longer wire, and then maybe you could wrap it around something that you are trying to protect, like a valuable. such as money. And then if an intruder was to remove the wire, the music would play, sounding an alarm. 147 is night music radio. I have the photoresistor connected, and I'm going to turn on the radio. And the music is loudest when the photoresistor is covered. If I have light shining on the photoresistor, the sound will stop because resistance builds up. But when I cover it, the music should play. The circuit can be temperamental, but once again, it's playing while the photoresistor is covered and light is not able to get to it. 148 is night gun radio. I replaced the music integrated circuit with the alarm, I say, and when I turn on the slide switch and turn on the radio, and the photoresistor is covered, the radio will now produce the sound of a machine gun. Although technically it's the circuit producing the sound, but it broadcasts it to the radio for its speakers to play. And this could be another good darkness announcer. .149 is radio gun alarm. I put a jumper wire between these 2 points, and with the radio on, I'm going to remove one end of it, and now the machine gun sound plays. This could be another good alarm circuit. And then to disarm the alarm, simply reconnect the jumper wire and the sound will stop. 150 is daylight gun radio. I replaced the R5 resistor with the photoresistor, just like for Project 146, but now the alarm integrated circuit is in place, and when I turn on the radio and then the circuit, when there's light on the photoresistor, the radio speakers will play a machine gun sound. When I cover the photoresistor or place the circuit in the dark, the sound will become quieter or stop altogether. This could perhaps be a good alarm to wake you up in the morning as soon as it becomes bright outside and light shines in through your window. So it would be ideal to place your circuit there. And then you could just place your radio elsewhere to wake you up. Project 152 is series lamps. I'm using the 2 LEDs, but I'm going to turn on the slide switch and both LEDs come on. They are wired in series. So if I was to remove one LED, or if one LED was to fail, the other one would fail as well. And an example of a real-life series circuit could be in an old-fashioned set of Christmas lights. Back then, they were wired in series, and so if only one bulb went out or was damaged, then all the other lights will go out, and it would also be more difficult to find out which light failed, since none of the others could work. 153 is parallel lamps. When I turn on the slide switch, both LEDs light, but if I was to remove one of them, the other LED will stay on. They're wired in parallel, so they each have their own path for current to flow through. They're not sharing the same path. And a good example of a parallel circuit is in a modern set of Christmas lights. Modern sets are generally wired in parallel, so that if one lamp was to fail, the others will remain lit, and it would also be much easier to find the one that has broke. And also, most lights in your home are wired in parallel, so if one was to go out or fail, the others will stay on. 164 is capacitors in series. With the slide switch on, I am going to hold down the press switch, and you'll notice that the C4 and C5 capacitors are included in the circuit. When I hold down the press switch, the red LED quickly comes on. Then when I release it, it will slowly go out. And you can notice that as I zoom in closer. The effect is better viewed in a dark room, but I'm just going to quickly demonstrate it the way it is. Now I'm going to turn off the slide switch and hold down the press switch again, then release it. Now with the slide switch off, the LED goes off much more quickly. That's because when the slide switch is off, both capacitors wired in series are included, and they will discharge much more quickly. It reduces the total amount of electricity the capacitors store. And this is opposite as to how resistors in series work. They do not, they kind of almost cancel each other out rather than combine the capacitance and allow more energy to be stored. For 165 capacitors in parallel, with the slide switch off, I'm going to hold down the press switch, the LED comes on, and now the C4 capacitor is currently included in the circuit. When I release the press switch, the LED will quickly go out. Now I'm going to turn on the slide switch, and now both capacitors are working in parallel. And so the LED comes on very quickly, but it takes a lot longer to go out because the capacitance is increased when the capacitors are used together in parallel, not in series. When they were both included in the series circuit, the LED went out faster since their capacitance was reduced. For this project, I am going to use a cup of water, of plain water, turn on the slide switch, and I'm going to stick the ends of both jumpers into the water. When I do so, the red LED comes on because the water acts like a conductor of electricity. And this could be a good visual water detector, as what the name of this project implies. Now, the more pure water is, the less conductive it is, but the more impurities it has, like drinking water, the more conductive it will be. Now, I'm not going to do it, but if for the next project, if I was to add salt to the water will be even more conductive, just to let you know. So salt water, like in the ocean, will conduct electricity a lot better than, let's say, maybe river water or water from your local water supply that you use for drinking and bathing. I'm going to turn on the slide switch and the green LED comes on. When I shine light onto the photoresistor, the LED becomes brighter. But when sorry that's hard to see due to the glare of this lamp, I'll just hold it directly over up high. But when I decrease the light supply on the sensor, the green LED goes out. The photoresistor controls how much current flows through the PNP resistor transistor to light the green LED. With this circuit, I am going to shine light on the photoresistor, and this time, the more light that shines on, the LED will turn off. And then when I remove light from the photoresistor or cover it, the LED will come on. It's now acting like a street lamp that comes on at night or when conditions are dark. The photoresistor is again controlling the current that flows through the NPN transistor, but it is reduced when there is light on the photoresistor, unlike when it is covered in the previous project. I now have the PNP transistor in red LED. Turn on the slide switch and it comes on. When I cover the photoresistor, the LED turns off. But when I shine light on it, the LED becomes brighter. the photoresistor is controlling how much current flows through the PNP transistor, and the more light there is on the photoresistor, the more current can flow through the PNP transistor. I'm going to turn on the slide switch, and this time when I cover the photoresistor, the LED becomes bright, and when I shine light on it, the LED turns off because it is now only allowing current to flow through when it is dark or when little to no light gets to the photoresistor. The more light that's shining on it, the more resistance there is, and the less current can flow through the PNP transistor. I am going to turn on the slide switch, and the red LED comes on. The lever on the RV resistor is all the way to the left. Now, when I hold down the press switch and move the lever to the right, the red LED will become dimmer while the green LED is brighter. It's not perfect, but when I move the lever back to the left, the green LED turns off while the red LED comes back on. When the adjustable resistor is on one side, in this case on the right side has little resistance while the left side has a lot of resistance. But if I let go of the press switch, then there will be less resistance on the left side, and the green LED will turn off while the red LED becomes brighter, or the other way around. Even if I had a lot of current flowing through the red LED when the lever is on the left, if I was to turn off the slide switch but hold down the press switch, the green LED will light up a little bit. And it turns off completely when I turn on the slide switch for the red LED. I am going to turn on this circuit, and the red LED is on. It becomes brighter when I turn on the slide switch, and even brighter yet when I push the press switch. Now I'm going to turn off the slide switch while still holding down the press switch, and the LED becomes dim again. When the slide switch is on only, the R3 resistor is limiting the current flowing through the red LED. But when I push the press switch, the R2 resistor is connected in parallel, and electricity is going to flow through it instead of R3. And R2 has less resistance than R3, and so the LED will become brighter. However, when I turn off the slide switch, all three resistors are included in the circuit, including the R4 resistor, and the current will be reduced even more. So all resistors are limiting the current flowing through when the slide switch is off.